having to get used to just verbalizing what I'm doing. So.
Awesome. Welcome back, Sam.
Keith is my second time here. Just finishing up CSX and starting coding.
Nice. Keith, right?
Keith.
Awesome.
Hi, I'm Julie. This is my first time workshop, and I'm going to
Awesome. Welcome, Julie. Nice to meet you.
Guys, my name's Sam. I'm using CSX. Code Academy.
Awesome.
Probably a couple times.
I'm Lydia, and I've used like 5 or 6 times, and I'm using Code Academy, CSX, Bootcamp.
Awesome. Welcome back, Olivia.
David, been here probably about 4 times now, I guess, and just going through CSX and then whatever Google comes up with.
Awesome. What was your name? Dave.
Brian, I made 3 or 4 times at Hotbirds and CSX.
Awesome.
Hi, I'm Karen. I've been here 6 or 7 times, and right now I'm using Python.
Nice. Python tutor, yeah. That's a good one. Awesome. And one more time, your name? Karen. Awesome. Welcome, everybody. We're going to get started. Welcome, everybody online. We're going to get started now. I'm just going to move the camera so you guys can see the board. Awesome. All right. Yeah. And just quick note for everybody in the room. We are streaming online here. So if you don't want to be in the online stream, just don't walk past the camera. It can't see you. It can only see me. Don't worry about it. I just like to note that for everybody out there. All right. Cool. Let's get started talking about recursion. I need an eraser. Awesome. Okay. So, before we get started with our regular old whiteboarding and all, let's talk about what recursion is. So, recursion is just a manner of repeating code. It's an alternative to looping. Anything that you can do with a loop, you can do with recursion and vice versa. Some things are better suited to being solved with recursion, whereas some things might be better suited to be solved with looping. It's really up to you. There's just kind of a difference in the syntax, and there's always this question, right, of when do I loop versus when do I recurse? And why would I care about learning an alternative to looping if I can just loop through anything I want to do? So looping is best for kind of envisioning the entire body of work that has to be done. Every single step of the process is really just kind of laid out line by line of what's going to exactly happen. Whereas recursion is best for envisioning work that must be done at any one point in time. So at any one point in an iteration, what is the work that needs to be done? And we're going to walk through a bunch of examples tonight about how these different approaches look. There are also multiple ways of doing recursion. So kind of just different syntax for solving the same problem and kind of a different mindset about how to solve the problem. So I like to talk about this in the example and like kind of a real world example as we go through the different situations we're going to encounter tonight. So let's think about it like when we walk from one side of town to the other side of town. Let's say we're walking from maybe our apartments over here, and now we're walking to our work building, right? There are different approaches that we could take to actually getting from point A to point B, right? One way, right, is that you could count how many steps it takes to get there and what direction you have to walk for that many steps, right? So I walk forward 180 steps, and then I turn left and I walk 30 steps, right? That's one way of kind of solving this problem of how do I get from my apartment to my work building. Maybe not, probably not what you're going to actually do in the real world, right? You're not going to count 180 steps, or you're not going to count how many steps you're taking every time, right? You want to be able to do other stuff in the meantime. So another way, right, an alternative way would be to kind of walk corner to corner and decide at each block what you should do next, right? So I've walked one block, now do I go left? Do I go right? Do I keep going straight? Or am I at the location that I need to be at, right? So this kind of represents more of the recursive way of thinking, right? Taking a large problem and breaking it down into similar but smaller steps until we come to a point where we just have to answer kind of one or two questions over and over and over again, right? Am I currently at the place that I need to be? No. So then now what do I need to do, right? Do I need to walk forward? Do I need to walk left, walk right? What do I need to do? And that's kind of the same thing that we're doing with recursion. So let's look at two different examples of writing the solution to this walking through town in code, right? So the first thing we're going to look at is the coding equivalent of counting steps, right? So that kind of first solution of we're going to count how many steps it takes and what direction we walk to count that many steps. And this is what this looks like. So before we walk through all of this code, right, we're not going to walk through it right now, but just looking at this, is it super intuitive what our steps are, what we're actually doing in this function, just by kind of taking a quick glance at this? Sort of. We have kind of we're declaring a variable, and then we're doing a loop, and then we're doing a different variable, we're doing a loop, and then at some point we're entering the building, but it's not super clear right away what's going to happen in this function. It's loop through town, eventually we're going to enter the building, at some point we're going to loop here. Basically what this is doing, right, is it's still taking a problem and breaking it down into steps, right? We're getting a bunch of parameters here, right? Me x, me y, end x, end y. So basically our starting coordinates versus the coordinates that we want to end at. And first we are calculating our east-west distance and basically going left or right for as many steps as we need to get to the point that we need to be at so that our x coordinates match. And then we're going to go north-south, right? We're going to go forward or backward, depending on where we started versus where we need to end up. And we're going to do that, and we're going to do a loop for each of those possible coordinates. That's fine. This does exactly what we need to do, right? This is still solving the problem. It's doing everything we need to do. Once we read it, we can kind of get a sense for what we're going to do here. But it's quite a bit of code, and it's not maybe the most clear-cut code. Here's kind of the coding equivalent of going corner by corner. Now, just at a quick glance, to me personally, this seems a lot more clear. Maybe not more clear in the sense that we don't necessarily know what each step is doing, but we get the sense that, okay, if we are at our building, we're going to enter it. If we're not in our building, we're going to recurse through town, and we're going to rerun this function until we're at our building, right? Now we'll break this down into even smaller steps, right? We're still getting the same parameters, right? Our starting coordinates and our end coordinates. But what we're going to do first is, right, always going to check to see if we're already at our building, because if we are, then we can just enter it. But otherwise, we're going to see if our x and our y, or if our starting x and starting and ending x coordinates are the same, by either our x is greater than or our x is less than. And if so, we're still going to go east or west first, right? Left or right first. And we're just going to pass a new parameter into our function for our x coordinate, depending on whether or not we are left or right of it. Once we don't hit these two, once we don't hit either of those if statements for our x coordinate, we're going to hit one of the other two statements for our y coordinate, right? So we're still going to go either north or south. We're basically solving this problem in a similar way, right? We still have to get from one point to another, and we either have to go forward or backward or left or right. But our code is a lot cleaner. Code is a lot more easily navigatable. Words are hard. Yes, we can navigate through this code a lot easier than we could in the other one. At least I think so. I mean, there's a lot going on here. We have two different for loop syntax that we have to look at. We have to declare new variables. There's a whole bunch of stuff going on here that we don't have to do in this case, right? We can just pass new parameters into our particular position, right? Either our x or our y, and we can just keep passing new parameters into that until we actually get to our building, right? Till we get to a point where our coordinates are equal. Come on in. So, two different perspectives here, right? Why do we care about learning these two perspectives? Other than that, the code is a little bit cleaner. Because it is something brand new to understand, right? What is the deal with this function calling itself? We're just passing in new parameters. Maybe we don't want to learn new things, right? We can just do this with looping, who cares? It's intuitive though, because when we think about everyday situations, we think recursively, right? We think about walking to our building or walking and taking directions, going kind of turn by turn. We do the same thing over and over again until we need to turn. We don't count 180 steps and then turn and count 30 steps, right? We walk block by block and see, do I need to keep going or should I turn here? It's a fundamental part of computer science. You'll find recursion in all different languages. It's something that exists out there in the world, so it's just good to know. It, again, has a functional programming mindset, so it treats data as immutable, right? So instead of what we're doing in our looping through town is we're taking our input parameters and we're actually mutating them, right? We're changing them around versus in our recursive solution, we're just passing in new parameters, right? We're not mutating the parameters we already got. We're just passing in new parameters to another instance of that execution context, right? Or to another execution context. Reduce complexity of iterate code, right? So this is really good for more complex examples. For once you start to get into a situation where you might need to loop through an unknown amount of nested items, right? If you need to go through objects and go through every property on that object, and if that's another object, you need to go into that nested property on that object. You don't know how deep the nesting might go. Recursion makes that a lot easier because you don't need to know. You can just keep recursing until you hit a point where you have no more nested items to go through. Because you're not checking for the end result, because you're not going step by step, you're just checking for the end result, and if it's not that end result, you're going to do the same thing over and over and over again. Handles multiple conditions with different actions. We'll look at some examples of that in a bit. So let's take a quick step back, right? Because fundamentally, recursion is when a function, somewhere in that function will call itself, right? So what happens when functions invoke other functions, right? So function foo, in function foo, we return whatever the output of invoking this function bar is, right? So if we're talking about our regular kind of hard part style, we have a lot of hard parts veterans here tonight, right? We have a bunch of things when we start running JavaScript, right? So we have this global execution context. And a space for all of our code to run. And then we also have a memory, right? A global memory space. And as we go through this, right, let's assume that at this point we have a bar stored somewhere in global memory as this whole function definition, right? And now we're defining this function foo, storing that in our global memory. And if we actually invoke this function foo, right, we'll get on our call stack, just keeping track of what execution context we're currently in, right? We start out in our global. And then if we actually invoke this function foo, we get a brand new local execution context with a local memory. And our function invocation gets pushed onto our call stack, right? So now comes the fun part, right? What happens when we get to this return line, Crystal?
If it's satisfied, it says the function.
What's that?
I said if I guess like if your parameters, I guess, CSX are satisfied, it exits the function.
Sure. So let's say we just ran this function foo, right? What does function foo do? What happens on this line, that the only line in that function? Returns bar, or what? Or does it return?
Bar function.
Yeah, the output of running that function, right? So the first thing we're going to do is we see, right, we need to return whatever the output of running bar is, right? So what happens when we invoke a function? Second. Oh, sorry.
Oh, no, go ahead.
I was just gonna say, does it get put to the call stack?
Yeah, it gets pushed on the call stack, right? This function invocation gets pushed onto the call stack. And what else happens, Sam?
Oh, and then you open up another execution.
Yeah, we get a new little local execution context with a local memory. And then bar does whatever bar is going to do. And maybe it returns out some value. And whatever bar returns out, once it returns out some value, what happens to this execution context?
Closes.
It closes, right? It goes away. Poof. And what happens to our call stack? It pops off the call stack, right? Awesome. And then are we done with everything out here in this execution context, in our foo execution context? Yeah, right? So this is just going to get passed back out here, right? Because we're returning whatever the output of invoking bar is. So now we just have value sitting out here somewhere. We're not actually doing anything with it because this doesn't have any code that's actually invoking this function. This function execution context just goes away, right? And it pops off the call stack. So we're left with just some value that's out here, and now our whole program is done. So we also get rid of all of this now. But basically, right, when we invoke a function, we get a new local execution context, we get a new local memory, and that function invocation gets pushed onto our call stack. Fundamentally, that's what happens when we invoke a function, right? And if that function invokes another function inside it, we create a new execution context inside of the scope of the current execution context we're in. And that function's call gets pushed onto the call stack on top of our first function's call, right? Because call stack, again, is first in, last out. So the first thing that gets onto the call stack, gets pushed into the call stack, is the last thing that gets popped off of it, right? Because we're going to do everything in this execution context before we can resolve this outer execution context. So fundamentally, that's all that's happening when we invoke a function, right? What happens when a function invokes itself? So let's get rid of all of this. All right. So now, in this case, right, we have a function definition for foo in our global memory, right? Just a function definition sitting there. Interesting thing about this function definition, right? What's going to happen if we actually have a line that invokes this function? Sam.
It's just going to keep going forever.
But walk me through it, though. Well, let's say we invoke this one time. What happens?
So you have your local execution context.
Cool. And local execution context and local memory, right?
And foo on the call stack.
Yeah. And what happens inside of this function? Like, what are we going to do when we actually run it?
Gonna execute. It's gonna call it execute foo again. So we're gonna have another local execution context for foo and foo on the call stack again.
Yeah. Great. What happens next, Mike?
Again, you're going to return foo, so you're going to open up another local execution context. You're going to push it on the call stack. And, yeah, return again.
Cool. Are we all tired of seeing that now? I am. So we're going to stop. But yeah, basically, right, this is going to just kind of keep calling itself. We have nothing else to say. This function does nothing but call itself, right? This is a recursive function. It's a bad recursive function, though, right? Because if we run this function as it currently is, we get maximum call stack size exceeded. Because there's a limit to how many things we can have on this call stack. And at that point, we will be sad, right? We'll get this error, and that's bad, right? So how do we prevent something like this maximum call stack size exceeded or stack overflow? Well, before we talk about that, right, this is kind of going back to our real world example that we're going to keep coming back to, right? This type of recursive function is similar to just kind of walking around in a circle over and over and over again and never actually seeing if you're at your building, just walking 180 steps forward, turning left and walking 30 steps forward, turning left and walking 180 steps forward, right? So this is just the cycle that you're going through when you don't have anything stopping you at your building, right? Or in this case, right, stopping at our destination, base case. So we need something in our function definition, in our recursive function definition, to say stop, right? Do something different now. We're done with all of our recursion. We can now do something else, right? Return some value, invoke some function, log something to our console, whatever the case may be. We always need a base case or potentially multiple base cases, depending on what your particular function is doing. In this case, right, we need two things to be accurate before we do something else, right? We need both our x and our y coordinates to match with the end x and y coordinates. So yeah, we have at this point a base case, and then how do we move toward our base case? Everything else in our function should be helping us move toward our base case. If there's something in that function that's not helping us move toward our base case, what's it doing in that function, right? What is the purpose of it? Maybe there is a purpose for it. Maybe it's, console logging something, at each iteration you're testing something out. But for the most part, right, everything else in your recursive function should be helping you somehow move closer to that base case. At each one of these if statements, we are checking to see if a particular case is hit. And if it is, right, we're doing that recursion and we're passing a new parameter, getting us literally one step closer every time to our base case. Till at some point, the only thing that's going to hit is that first if statement hitting our base case. So, great. Common themes in recursion, right? Basically, with recursion, we want to take our problem and break it down into similar but smaller steps and smaller problems that we can solve, right? In our recursive case here, we are, at each iteration, we're breaking it down into smaller and smaller steps. Are we to the left? Whatever. Are we to the left or are we to the right of our x coordinate, right? Are we north or are we south of our y coordinate? And going through each of those steps every single time to figure out, get us one step closer to our base case. Eventually, we reach a problem that's simple to solve, right? Again, walk to a corner, left or right, north or south, east or west, right? Walk to a corner, do that same thing. It's repetitive. It's boring. That's why I keep saying it over and over again, because it's repetitive. Combine all of the smaller solutions to solve that bigger problem, right? Walk one block at a time, walk one step at a time, and then eventually you get to where you're going, right? So now we're going to go through kind of different ways of solving the same problem. Because like I mentioned before, there are different ways of writing recursive functions. Some of them better than others, some of them just more suited for different types of problems, right? So the same problem that we're going to solve, and I'm going to take up some of this space here to write these instructions so we don't have to keep referencing them. Our example is we're going to write a recursive sum function. So given a positive integer as an input, return the sum of all numbers from 1 up to and including that input. So for example, if our input of 3, if our input is the number 3, our output should be the number 6, right? Because what we're doing is basically summing all the numbers from 1 up to and including the input number, right? So 1 plus 2 plus 3 is 6. And again, yes, we can do this with a loop very easily, but we're here to learn recursion, so we're going to do it the hard way. Yeah. So let's talk about it, right? Real quick, I'm going to write all this stuff up here. So we have our input is a number And our output is also a number. And kind of the rules or instructions for this output are sum of input, sum of 1 up to including input number, right? So this is our goal, right? Getting an input number, we want to output a number that is the sum of 1 up to and including that input number. So let's talk about it. You guys tell me, what is the base case for this function, right? So what is the, well, actually, before we even talk about the base case, no, let's talk about the base case. I lied, right? What is the base case for this, right? What is the end result that we are now going to return from? Anybody have thoughts? Olivia?
If sum equals 6.
If sum equals 6?
No.
Because we want to be able to put any number in there.
Okay.
6 was 6, or 3 was just like the example number.
Yeah. So
Right?
If the sum equals the input number.
If sum equals the input number, interesting. So one way of doing it, right, is if, what?
Did I read that right?
So sum shouldn't be the input number, right? Because the input number is just we're gonna take 1. We could start at 1 and add basically if our input number is 3, we're gonna say 1 plus 2 plus 3, right? So go up to the number 3 and add all those digits together. So it wouldn't be if the sum is our input number, but maybe if if we're doing a loop, if our counter, right, or something like that is our input number. Parker? Okay, cool. Yeah, so that's totally one way of doing it. How would we approach that then? So if we have a counter somewhere, how would we go about doing that with recursion then? What's our recursive case? If we're saying, I don't know why I erased this. If we're saying our base case is counter is input number, what is our counter starting at? 1 or 0?
It doesn't matter if you're adding 0.
Fair. Yep, it doesn't matter if we're adding 0 to it, right? So we could start at 1, we could start at 0, it doesn't matter. Let's say we're starting at 0, right? So start counter at 0. And what do we do from there? So where does counter, so let's talk about this, right? Let's write our base function, right? So we have our function sum recurse, sure. What parameters do we need in here? We need any parameters, right?
Your input number.
Input number, right? So is our counter a parameter, or is it getting defined in our function definition or somewhere else?
So we can set a default case.
So the default case for it as a parameter, we can have an input case for, we could have it as our input. Why would we not want to have it inside our function definition?
Because you can only return arguments.
Go say more.
So when you recursively call the function, when you're recursively calling it, you're returning the argument as a parameter for the new function itself.
Yeah, and so basically every time we recurse, right, we would open up a new local execution context, which would redefine what counter is every time, right? So every time we'd be restarting at 0 if we defined our counter inside this function, right? So we can set counter out here. We can use some fanciness to give it a default if 1 isn't passed in, right? Yeah.
Question for you, just so I get the wording right, is that when it comes to a return statement, is it returning an argument and then still, even though it's recursion is returning an argument and passing it as a parameter?
So yeah, so parameter versus argument, it's a good question. A little off what we're talking about, but it's totally fine. It's quick quick answer, right? So when it's the label for it, it's the
So
parameter.
it still works the same
When it's
way.
when you're actually invoking the function, you're passing it arguments.
So it works the same way even though it's recursive.
Yeah, I mean the terminology stays the same there. Yeah. Okay, so before we go too much deeper into this particular into this particular discussion, this is something that you could this is a way that you could definitely solve this problem, where you would just continue your counter up and have your input number come in, and if you hit your base case, which is that the input number is the same as the counter, then you return whatever the sum is. What do you return there? William? It's okay, I needed a cough break anyway.
I'm very sorry.
All right, so yes, so we can do certain things here, right? We can do this as a totally valid way of solving this problem. But let's talk about the way that I have it in the slides here, which is a bit different. But again, it goes to show, right? We can talk about many different ways to solve this problem. I particularly use this first item as a base case or this solution because I didn't want to have any additional parameters, right? I don't want to keep track of any additional parameters at this point. So I am assuming that I'm only ever going to get one input parameter, or one parameter, and it's going to be our input number. So addition though is commutative, so order doesn't matter. So we could go from 3 to 2 to 1 instead of 1 to 2 to 3, because addition, it doesn't matter what order you do the addition in, it's going to come out to the same number. You could do 2 to 3 to 1 if you wanted to, but that would be a very silly way of doing this. So instead of keeping track of an input number of a counter somewhere here and incrementing it, we're going to keep track of a number as our input number. Whew, man, my brain just lost it there for a second. Cool, yeah. So our base case is going to be when our input number is 0, we return something, and we'll see what that looks like in a second. Otherwise, we're going to return n plus the return value of the call with n minus 1. This is a lot of words, but let's look at it in code, right? That's what we're here for. Before we look at that in code, though, let's talk about how to return a value out of a recursive call. So we return the invocation of the recursive call. That's one way, that's how you would do it, right? You return an invocation of a function, which eventually will return whatever the output of that function is. We can connect work in our recursive call to our next recursive call, so we can do kind of additional things in there. We don't have to just return the invocation of the function. We can do addition and subtraction, any kind of other arithmetic that we need to in the actual return statement. And it'll just wait for whatever the recursive function definition is to be or function invocation is to return a value before it does that addition or subtraction. We can return the appropriate value when hitting our base case and passing the value from the deepest execution context all the way back out. Remember when we looked at our first example up here where foo invoked bar, but foo just returned whatever the output of bar was? We just basically passed through that first execution context, whatever the inner execution context returned. And it's the same idea here with recursion, is that you're continually opening up execution context until it eventually balloons back out with the value that you're expecting at each iteration. Don't worry, there's not going to be more of me talking. It's going to be more of you talking. So here's our first solution. We're going to keep track of a total, right? Because this is the other bit of the equation that we didn't really talk about when we had our little discussion there, right? Is how do we keep track of our total? Where do we keep track of our total? In this case, we're going to use a global tracker to keep track of our total. So start me off here, David.
So this is defining a variable in global execution context called total, and setting it equal.
Cool. Very good. Thank you, David. Total is 0. Next up, what are we doing, Brian?
We're going to declare a function summary,
Yeah, totally. Oh, thank you. Thanks. All right. Awesome. What are we gonna do next? Keith.
We're gonna call some range.
Biggest execution context ever. Awesome. Yes, exactly. Some range. 3. Cool. What's the first thing we're going to do inside this function, Olivia?
We are going to declare our base case.
Check our base case, right? And what's our base case?
If
Actually, before we even do that, what are we going to do before we do that?
we're going to declare our parameter none and set it equal to 3.
Yeah, awesome, right? We're just going to handle that argument, parameter, whatever. Yep, but then we're going to check our base case. What's our base case?
If none is equal to 0,
And what is num right now?
none is 3.
So is num equal to 0?
Then return total.
But it's not, right?
Yeah,
No.
yeah, yeah.
So then what are we going to do?
We are going to add total plus no.
And what is num right now?
3.
And what is total right now?
Total is. Do we know which one it is? Sorry. Oh, my bad. Sorry.
Yeah.
Total 0. Yeah.
How dare you?
Okay, so total 0. So yeah, they don't. So then we're going to we're going to return the value of invoking some range, again, passing in 3 minus 1.
Awesome. Excellent. Thank you, Olivia. Some range. Passing in the input of what?
None minus 1, so 3 minus
Which is 2. Awesome. Yeah. Great. What happens when we invoke this function? Parker.
Gonna check the base case.
Before we do any of that, what happens just when we invoke a function?
Declare the parameter num, the local number.
Before we even do that, what do we get?
Are we gonna call some range?
Yep. What happens when we invoke the function? New. Yeah, new execution context with the local memory. And what happens up here?
Put another call step.
Yeah, pushing on the call stack, right? Some range 2. Awesome. Yes, and then we are going to handle our input parameter, which is going to be num. What's num right now, Parker? 2. And what's our base case?
Num equals 0.
And what is num right now? 2 is not 0, right?
That's right.
Awesome. So now what are we going to do?
Add num to total.
And what is num right now? 2, right? 2 plus 3, 5. Then what are we going to do?
We're gonna return some range.
Num minus 1 is?
1.
Awesome. Thank you, Parker. What are we going to do next, Crystal? So we invoke this function. What happens when we invoke a function?
What's the terminology for it? I guess we're starting all over.
Yeah, new execution context, right?
Execution.
Yeah, new execution context, which is new execution context with local memory, and what happens to our call stack.
So then it's now some range 1.
Yeah, some range 1 gets pushed onto the call stack, right?
Some range.
Yeah, awesome. All right, get more people involved in this. Sam.
Oh, yes.
Yes. What are we gonna do inside this sum range with the input of 1? What's the first thing we're gonna do?
Which
Where are we? Sorry. Some range.
Some range with the input of 1.
Oh, okay. So if num, we're checking to see if num, if 1 is equal to 0 and it's not.
Yes. What are we doing if it's not?
So
Or since
then
it's
we are total is equal to 0 plus 1.
0 plus 1?
Oh, sorry. The total is something else.
Yeah.
5.
Yeah. So now it's 6, right? Then what do we do?
And then we exit. Oh, so we return. Sorry.
No
We
worries.
return some range 6 minus 1. So that's
6 minus 1? Num minus 1. What's num right now?
5. Oh.
We didn't handle our input parameter. Whoops. My bad, y'all. Num is 1 right now, right? Num is our input parameter for the function.
Oh.
So num is our input parameter for the function. So num is 1, and then we do num minus 1. What is num? Num is 1, so we do 1 minus 1, which is 0, right? Awesome. So before I draw that up on the board, on my Karen. Yes. What are we doing?
We are creating another local. Oh, we're
Yeah, no?
creating another local.
Yeah, awesome. With our little baby local memory, little baby execution context. What happens to our call stack? Awesome. And let's just keep going here. What do we do?
And then we're going to check if num is equal to 0.
Before we check if num is equal to 0, because I forgot to do this last time.
Num to
Yes. So num as 0. Now we're going to check if num is equal to 0. Is num equal to 0?
then we return.
Yes. So we return. And what is total right now? Return 6. All right. What happens when we return out of a function? Pops out the call stack, right? What else happens? Boop. To our execution context. Goes away. Yes. I like the enthusiasm. Yes. Goes away, right? So now we have out here some range, and we want to return some range, and some range gets replaced. The indication of some range with the input of 0 gets replaced with 6, right? Because that was what the output of returning some range was. Now we return that back out of our function, right? So now our execution context with the input of 1, right? Context for the sum range with the input of 1 is done, right? So pops off the call stack and the execution context goes away. And now in our execution context for sum range with the input of 2, we have 6. So we just return out 6 here. Now this execution context goes away. Poof. Awesome. Pops off the call stack, right? And finally, sum range, the input of 3 goes away, and we are left with 6, pops off the call stack, and life is good, right? We're all happy. We've made it. Yeah, so we can start seeing that, like, recursive functions, while at first might look a little bit scary, it's a little bit unclear what's actually happening, right? We saw those different recurse through town function invocations, and it was never really clear what's happening at each step of that. But as soon as you start mapping it out and start drawing it out and really start seeing how each of these function invocations is really just like any other function invocation. You need to just wait until the most inner execution context resolves, till it gets popped off the call stack, and then you can kind of balloon your answers back out, right? Balloon your results back out through the execution context, just like you would with any other nested function execution. Mike.
So you may have went over this part. So when you got into the call stack, you got all the way up. So you got into the local execution context at the end. Did num have access to the global memory total, or did it have to keep pushing that back through each collapse of the step?
Got it. Yeah. So basically, the way that kind of the memory value label looking for is going to work. Like the scoping works. Scoping is the word I was looking for. Damn. Yeah. So the way that scoping works is if it doesn't find it in the local execution context, the local memory, it'll kind of keep going out to see, is it in this execution context? No. Is it in this one? No. Is it in this local memory? No. Oh, it's all the way out here. Okay, now I'll update that one. That's why you can have, right, num declared multiple times in the kind of nested execution context, because it'll never think that num is 2 down here, because it's going to look in its closest execution context or its closest local memory before it goes out to the outer scoped memories.
I was just making sure.
Yeah.
So we had like a super long recursive thing. Would it be better memory-wise to declare the parameter? Not having to check. I mean, it's going to check farther and farther every single time that adds a new recursive.
Excellent question. So there are a few things that we maybe don't like about this approach, right? One is anytime there's some kind of globally declared variable that you're constantly updating is not necessarily best practice, especially from like a functional programming mindset, right? So not maybe the ideal solution, but is a good solution for just starting out with recursion, especially because you don't have to worry about figuring out how to pass total through and deal with more parameters than you really need to. So this particular solution is really good for like just starting out with recursion, not worrying about kind of space complexity or things like that. But we're going to look after the pair programming part about like other solutions, other ways to solve this problem. That do give you kind of more space efficiency and just different ways of solving the problem. So yeah, observations about this though, right? The last call to the recursive function triggers this balloon effect or bubbling effect back out to the outer execution context where you actually get the return value in the end. And the initial function call is the last one to complete. Obviously, we all know how that call stack works, right? So how do I approach a base case if the input is not a number, you ask? Yes, good questions. Right, so instead of decrementing numbers and things like that, what if I'm passed an array or a string or an object? How can I use these same principles to get to my base case, right? So for arrays or strings, right, you can still use numbers to accomplish this, right? You can move through the indices of an array. You could also chip away at the array length, right? So you could always pass in just a new array with less items in it, right? You could slice the array, slice out the items you've already dealt with, and pass in any items that are still remaining. Multiple ways of dealing with that. Same thing with strings. You can, pass through the index or deal with the indices in some way so that you can move from beginning to end. In the end, you're still just kind of chipping away at whatever your input is, right? Chipping away or moving through your input in some way so that it's getting you one step closer to the base case. Objects, similar concept, right? Going through properties on an object or doing something with an object and basically adding properties like setting them to null, using Booleans for true false, right? Using different same way you would use an object for anything else, right? And kind of can do those things. So recursion is not just for numeric inputs or anything like that, and it's not best suited for anything with inputs. If you're familiar with kind of data science or data structures at all, linked lists are great things to use recursion for. Binary search trees, different data structures like that are really well suited for recursion, because they can have an unknown depth, right, or an unknown length. So now that you have all the tools that you need to learn recursion, right, we're going to do some pair programming. So these are statements here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, right? Or 8 of them this time. 8. Okay, so give yourself a score from 1 to 8. You get a point for every sentence you say yes to, right? We're going to line up around the room and we're going to pair everybody up. So starting back where Parker is. Parker, raise your hand. Starting back where Parker is, those are going to be 1s. 2, 3, 4, 5, 6, 7, 8, 9, all the way down to Julie at the end there. Julie, raise your hand. Yay! Yeah, so line up around the room. Don't worry about grabbing your stuff right now. Just give yourself a score, line up around the room. Anybody online that is interested in pairing, please feel free to put your score in the chat and I will pair you guys up.
Could be a 7.
Cool.
But just when I think about callback stuff, but walking over the 6th corner.
Awesome.
So that's the last.
What are you like? Good. How you doing? You good?
You got that?
Five, six.
I don't think he feels like he needs to come into the
Wait,
He's starting the program. He got in starting on Monday. Yeah.
All right. Sweet. Harry?
I got 0.
That's okay. You just still had. All right. Cool. So 2. 2?
Yeah.
Oh,
Two
yeah,
or three.
2.
She's
2.
counting.
Oh, I'm
Yeah.
counting off. Right. So you guys 2. You guys 2. Two. 2. 2.
Oh.
2. 2. I love even numbers. Though if you want to pair, you're encouraged to pair. All right, cool. So grab your stuff, sit next to your partner. You will only need one computer between the 2 of you. Did you bring your computer?
Yeah, my computer's not like set up.
Did you bring a laptop?
Sorry.
Okay. I don't have a charger though. But okay. I think mine's fully charged. Okay.
So, saving anything, any of this.
Where do you want to go?
information
No, I'm right here. Oh, well, there's I can.
Is it ever, sorry, what?
Like now.
Okay.
It's like you just call them, like, save their-
Well, so data saving is different from the call.
Okay, yeah. So is any of this stuff on the call stack and change like or is that still staying?
Yeah, it looks like
It's all, well, so total is the only, like,
Yeah.
in terms of data saving, in terms of like variables and stuff like that, total is the only thing living, other than the definition of summary, is the only thing kind of living in that global context that's available.
And that's all the way at the bottom of the stack where you guys now.
Yeah, so I'm not totally sure in terms of like the
just like